Heisenberg's uncertainty principle. In order to understand the conceptual background of the Heisenberg uncertainty principle, it is important to understand how physical values are measured. In almost any measurement that is made, light is reflected off the object that is being measured and processed. The shorter the wavelength of light used, or the higher its frequency and energy, the more accurate the results. Heisenberg himself encountered such limitations as he attempted to measure the position of an electron with a microscope. As noted, the accuracy of any measurement is limited by the wavelength of light illuminating the electron. Therefore, in principle, one can determine the position as accurately as one wishes by using light of very high frequency or short wavelengths. However, the collision between such high-energy photons of light with the extremely small electron causes the momentum of the electron to be disturbed. If a photon has low energy, the collision does not disturb the electron, yet the position cannot be accurately determined. Heisenberg concluded in his famous 1927 paper on the topic, "At the instant of time when the position is determined, that is, at the instant when the photon is scattered by the electron undergoes a discontinuous change in momentum. This change is greater for smaller the wavelength of the light employed, that is, the more exact the determination of the position. It is mathematically possible to express the uncertainty that Heisenberg concluded always exists if one attempts to measure the momentum and position of particles. First, we must define the variable x as the position of the particle and define p as the momentum of the particle. The momentum of a photon of light is known to simply be its frequency, expressed by the ratio h by lambda, where h represents Planck's constant and lambda represents the wavelength of the photon. The position of a photon of light is simply its wavelength, lambda. In order to represent finite change in quantities, the Greek uppercase letter delta or delta is placed in front of the quantity. Delta P is equal to h by lambda. Delta x is equal to lambda. By substituting delta x for lambda in the first equation, we derive delta P is equal to h by delta x. Delta P delta x is equal to h. Note, we can derive the same formula by assuming the particle of interest is behaving as a particle and not as a wave. Simply let delta P is equal to mu and delta x is equal to h by mu from de Broglie's expression for the wavelength of a particle. Substituting in delta P for mu in the second equation leads to the very same equation derived above. Delta P delta x is equal to h. This equation was refined by Heisenberg and his colleague Niels Bohr and was eventually rewritten as delta P delta x greater than equal to h by 4 pi. What this equation reveals is that the more accurately a particle's position is known, or the smaller delta x is, the less accurately the momentum of the particle delta p is known. Mathematically, this occurs because the smaller delta x becomes the larger delta p must become in order to satisfy the inequality. However, the more accurately momentum is known, the less accurately position is known.